Homework is back. I think the average was like 90, so. How are we doing on sound? Fong, microphone is good? Yeah, okay. If the key is not up, it'll be up soon. And then I'm gonna try my hardest to get you that third homework today, if not tomorrow. And I'll email that out. What else? Is that it? And then our first exam is a week from today. Okay. So today we're going to dive in a little bit deeper. You guys have not had like physical chemistry, right? No. Okay. So do you know the four-ish kinds, five-ish kinds of chemistry? That probably should have been my very first slide in this course on chemical principles. But so if you were to go to graduate school in chemistry, what are your bins? There's organic, physical, analytical. Yeah, so analytical chemistry, that's what I was trained in, and so we measure stuff. And organic and inorganic people, they make stuff. Physical chemists, they measure stuff too. So physical chemistry this is going to be kind of a few lectures on physical chemistry and describing in more detail how the atom moves around the electrons are arranged around the atom. So today we're going to derive the Bohr radius, derive the Bohr energy levels, talk about wave functions, and talk about probability distribution functions. Have you guys seen this kind of stuff before? What have you seen before? When did you see wave functions?
Quantum mechanics.
And that's a degree requirement?
Yes. Yeah. Prereq for this.
Prereq for this. Okay. And that's a nano course? Physics course. Okay. So, okay. Okay. Well, hopefully it won't be too redundant, but let's dive right in. So if we have a proton and an electron, there's a couple forces that we can think of are existing between them. One is our old friend, the Coulomb force, which we've seen before as K, the square of the charges, times R. This could also be Z if this is anything other than a hydrogen, right? If this was, because that is going to scale as the number of protons increase, right? The other thing that we can think of as happening is the centripetal force that is on this, if we think about it being in a fixed orbital, right? And so that is mv squared times the radius, right? And so since we assume, well, not assume, since we know that this orbital is fixed, these two are equal to each other, right? And so then we can simplify this a little bit more, and assuming that we're just in a height, I'm sorry, that should have been squared. That we're in a hydrogen atom, so we can drop that. Okay. And then if there's one other thing that we could perturb in this system, if we multiplied both sides by 1/2, what do we have then? Kinetic energy equals kinetic energy. Okay, so let's hold on to that for a little bit. The other kind of way of thinking about this is the momentum of the electron. And so that is m mass velocity times the radius is the momentum. I should be consistent with my R's. Momentum of electron. Okay. And so one of the, kind of landmark thoughts on describing the location of the electron was when Niels Bohr realized that these were quantized, right? And that these were a function of the different orbital arrangements, the orbital energy levels, and that this could be set to Planck's constant times the orbital energy times the principal quantum number over 2 pi, because, and 2 pi normalizes it for the sphere. So this is, you'll also see this written as h bar. That's a horrible h. Okay. And then we can rearrange this for velocity. ME is just mass of electron. And the other thing we can do is write this radius sub n, just indicating that this radius changes as a function of principal quantum number, right? Okay. So what we can do then is substitute this back up into this equation. And forgetting the 1/2 for now. Okay, so that was just our momentum-based expression that relates the momentum to Planck's constant back into our original expression that was relating the Coulomb force to the centripetal force. Okay, so we can cancel some things out. I'm sorry, I missed yeah, this is squared. So when you solve this, okay. So this is the mass of the electron, which is 9.1 times 10 to the negative 31st kilograms. And h bar is 1.06 times 10 to the negative 34th joule seconds. And our K we've seen since the beginning of class. Newtons meter squared per Coulomb squared.
Professor?
Yeah.
Why don't we see h bar as squared?
Thank you. Yes. And what else do we have? E we've known since the beginning of time, and 1 is there. Okay. So you have to revert back to fundamental units in order to get this to cancel in terms of, because in the top you've got joules and newtons. So go through and convince yourself that this works. So if you convert joule seconds to base units, you get that squared. And then if you convert down here, your K, newtons meters squared over Coulomb squared, it's kilogram per meter, kilograms meter per second squared. So that's your Newton component, meter squared per Coulomb squared. So this is just helping me get rid of converting all of this to base units. Then you've got a coulomb squared, and you've got a kilogram from your mass of your electron. Okay?
Is the top value supposed to be H bar?
Yep.
So, how did the samples go to the development?
This is converting newtons to base, converting to,
Wait, is it converting joules to base?
yes, converting joule seconds to fundamental units. So coulomb squared, kilogram, kilogram, meter, 1 meter, and seconds, seconds. Wait, I've got an extra kilogram. Oh, no, this is kilogram squared. So I got rid of all of my kilograms, and I'm left with only 1 meter. Okay? Meters squared. Because what's that? We're good?
3 meters on the bottom.
3 meters on the bottom, which, yeah, so we've got 1 meter on top. So we're left with 5.3 times 10 to the negative 11th meters, or 0.53 angstroms, which is the Bohr radius at principal quantum number of 1. Okay? Easy breezy. So what about the energy then at that level? Let's see, let's maybe go back over here. Yeah.
Why is momentum MDR instead of just MD?
Angular momentum.
Angular momentum, thank you. Okay, so remembering this, that our total energy is potential energy plus kinetic energy. And we know from here that kinetic energy is 1/2 k squared. And in this situation, we're writing our potential energy as negative because of this potential difference, right? And so this is going to be a negative ke squared over r. So this is just a simple negative 1/2 squared over r. Okay, and we know we just solved for r, right? And we know our k, we know our e, and so then this becomes negative 2.17 times 10 to the negative 18th joules, which is often written in electron volts. Okay? But what am I kind of missing? Like what if we would have started here and kept our z and propagated the z through the entire system? Right? This is only true at hydrogen, right? So what if you had lithium? Going to be more or less energy? Less, right? You're farther away, less energy. Lithium, the valence electron or lithium or calcium is going to be farther than hydrogen. It's going to be less energy. So if we would have, let's see, Yeah.
So are you saying that that means it would be harder to ionize hydrogen than lithium?
Yeah. Yeah. Yeah.
Even if lithium only has one electron?
This is talking about a single electron system, right?
Yes. A hydrogen-like system with an electron in the n equals 2 or n equals 3 or n equals higher principal quantum number. Right? Yeah.
Wouldn't the energy fluctuate from one atom to the other based on the protons that you put?
Absolutely. That's what this Z is.
Oh, I see. Oh.
Yeah. So Z is the atomic number. Yeah. Yeah.
So you can't treat that as a constant for any atom. It has to be calculated.
Not necessarily. So if we would propagate that through, you would still hold on to this. That constant.
So why is a single electron system for lithium easier to ionize than a single electron system for hydrogen?
Because the electron's farther away.
Why is it further?
So maybe lithium's not, maybe I shouldn't have said lithium, for a second principal quantum number. Or if you look at the periodic table, lithium is below hydrogen, and so it's then n equals 2, right? So forget lithium, n equals 2 or n equals 3 or n equals, just go down your alkali metals, right? Because you're increasing the R, so you're dividing by a bigger number.
So it would be, but that wouldn't count as it being a multiple electron system, right?
Yeah, exactly. You're still thinking of it as a hydrogen-like system, which is kind of a lie, right? It can't. I mean, of course it's not. Lithium cannot. Lithium is lithium and hydrogen's hydrogen, but it's a simplified way of modeling it.
This experiment.
You should ask. Yes, you ask. So this is all like these are like, you could say this is all lies, right? And so, but way before, I mean, people were doing this at the same time, and then, right, people started looking at absorption spectroscopy. So if you would put hydrogen and just absorb white light through hydrogen, you start to see these lines where a very narrow line, right, where you start to get this absorption. Similarly, if you took hydrogen and heated it up and did atomic emission spectroscopy, you see these lines of emission, right? And where hydrogen gives off these very specific lines. And you can do the same thing with every element on the periodic table, right? And they always have these very tight, and so this could either be emission or absorption, depending on what your experiment is. You're either putting energy into it to do emission or passing light through it, and you always see these very narrow lines that are like, you know, resolved to two decimal points. I mean, there's really no width to these at all. And so what people looked at, this is an equation called the Rydberg equation and the Rydberg constant. And so what people, and this was one of the first ones that they saw, and it's actually, you're looking at transitions to the second principal quantum number. And so you see these very specific lines that correspond, for example, the 4 to 2 is at 486 nanometers. 3 to 2 is less energy, right? You're only going between two quantum numbers. And so it's a longer wavelength. 5 to 2 is even bluer still, right? And so you can make this, determine this constant, which goes back to, you know, basic principles, Planck's constant, et cetera, and predict. And so then once people got this, they could start to predict for others. And it wasn't until A lot of these, so your bigger elements like cesium, cadmium, it's hard. How do you do this kind of experiment, right? How do you do emission or absorption with those heavy elements? And so the only way to do that is to get them really, really hot. And so you have to start to get up to 10,000 Kelvin, and so people started using inductively coupled plasma. And so, but the theory matched the experiment very nicely for those larger elements as well. So ICP came on in like the 70s, and people started being able to observe these lines. Yeah.
This is, I guess, slightly beyond topic, but how does something like that work? Is it just a rapid AC?
Yeah, it's an RF actually. So you take an inert gas like argon, which generally does not have any ions, and you invert your RF field really quickly, and you initially you spike it with some ions. Yeah, and so then once the argon starts to be ionized, it'll circulate in your oscillating RF field, and you start to smash those argons together really hot, and so it goes up to like 10,000 K.
And then eventually it'll ionize your signal.
Yeah. So you're using the argon as an energy source. It's like you can think about it as your fuel for your plasma. The argon creates the plasma, which creates a lot of heat, and then you blow you atomize, essentially like you vaporize your transition metal into that. So it's the same thing as when your pot bowls over on the stove and the flame goes from orange to blue, right? You're doing atomic emission, but here. Because when you look at the Boltzmann distribution, it's relative to e to the negative t, right? So temperature has a really important impact on how many are in the excited state, how many atoms or what percentage are in the excited state. So this actually came a little bit later, even though this is if you're going to the principle to n equals 1 ground state. So of course these are all shorter wavelengths, right? So this would be, for example, 2 to 1, 3 to 1, 4 to 1. This number is getting smaller in nanometers, implying more energy, right? So all these different series, and then this is the Lyman series. This one, I guess, is called the Balmer series, and there's all these different series where you go to different from X to your favorite principal quantum number. Yes?
Per centimeter, or
Per meter, this is, are my units off? I have to look it up. I would probably trust this more than this, but yeah. Okay. Yeah, so just bear this in mind that when you start to get to other atomic numbers, does this make sense that you have more energy as Z gets bigger? Right? Why? It makes sense that it decreases as this gets bigger, but why does the energy of that electron increase with Z? You've got more protons, right? Okay. Okay, so now we good?
I have a question.
Yeah.
When you're talking about the negative, it's how amount of energy required to release the electron from the n equals 1 shell, right?
Mm-hmm.
So the more negative it is, the more energy it's required to remove it.
That's right. Yeah. Yep.
Professor, what was the question?
The question was when you have the energy between the proton and the neutron is negative, and so the larger negative value that is, the more energy is required to release the electron. Yes. Yeah. Okay, so wave functions. So of course we know that these are kind of a lie, right? And so the wave function is a relationship that describes in better detail the relationship of where this electron is located, okay? And so the one thing to bear in mind is the de Broglie wavelength that you've probably seen, and that's the notion that all things have a wavelength that have a momentum. So here, this is not the angular momentum, right? So my wavelength when I'm walking, right? That blew my mind the first time I thought, like when I'm driving 70 miles an hour in my car, that there's some wavelength associated with that. And so the shape of when we think about an electron as a wave is described as psi, which is the wave function. When I was in high school, I used to do phlebotomy, and so I would like draw blood from people. And so when it was in the emergency room, there would be, this board where it would be patient's initials and like time in and diagnosis. And anytime, and it would be things like, HA for heart attack or ST for stroke. And anytime it was a psychiatric emergency, they wrote that, psi for like for psychiatry. And and so psi is our symbol for psychiatric wave functions. Yes, it is fitting. God, I really struggled with physical chemistry, so it really is just dessert. I had that now I have to teach it. So let's think about some of the features of a wave function. The first is that it is single valued. And so what does that mean? That you can't have the electron can't be in two places at the same time, right? Two positions concurrently. Second is that it's continuous. So it's defined at all positions. It approaches 0 at high R, right? So that's just saying that the atom is finite. Again, it approaches 0. We'll look at the end where it actually is 0. 4, if you integrate over all space,
So, you say pi r or at high r?
at high R. Yeah, at far distances from the nucleus, at large radii, the atom is, which is saying that the atom is finite. So this is saying the electron is here. The electron is somewhere. Why do we have it squared here? Probability. So what if you had a situation where your wave function looked like this, right? Where it's the wave function. So this kind of is saying negative probability. And so people tend to think about this in terms of it's squared. So it looks like this. Yeah.
Does that mean if we're trying to get a number out of the wave function, we would take the positive square root of the square of the wave function?
Positive square root. Oh. So you're saying if you were given the probability density function and you wanted to convert back.
Actual values.
Yeah, I think so.
Like we keep the x-axis and everything, and just our magnitudes and then stretched by square root.
Yeah. And finally, that if you have wave function 1 and wave function 2, and you integrate over all space, that is 0. So that's saying that these are orthogonal, that they're unique. Okay. So on that probability density function, I'm missing a term. If we were to think about the radial probability distribution, radial probability density function, what do you think I need to add? So this is telling me, if I imagine a sphere, right, that probability density function is telling me the likelihood of it to be at any point, right? So when we really need to think about is 4 pi r squared. So that's the likelihood of it being at any given point on the surface of a sphere, right? This also gets rid of imaginary numbers. A lot of times these will have, so I emphasize the negative nature here. You're getting rid of these negative probabilities, but as these become more and more complicated, you start to have imaginary components. Okay. So one of the first example that people generally walk through is the notion of if you just had a so-called particle in a box where energy is increasing, and this ranges from a value of 0 to a, and this is x. So outside of this well or box, you have infinite energy. Inside the box, you have 0 potential energy. So the particle is trapped, right, energetically. Your assumptions, there's no forces acting on the particle inside the box. It's a completely closed system. The particle can move. It has to move. It cannot be at rest. It must have energy. So I'm going to skip the derivation, but for the simplest situation, the equation again, where A is this kind of maximum dimension and x is your point at any given time. Did anybody read the chapter on this in the reader? I thought it was one of the most clear treatments of this that I've seen. It's kind of weird how that chapter, it starts off with the wave function, and then like later into the chapter it starts talking about electron configuration, like what we did at the very beginning. That doesn't seem entirely intuitive, but their description of the wave functions was pretty tight, I thought. So this is what these wave functions will look like at different n values. And then the corresponding probability density function. So n equals 1, n equals 2, n equals 3. And you can plot that to convince yourself. But of course, we're not only concerned with n, right? We're also concerned with the other quantum numbers. And so those are also L, your S, P, D, and F atomic energy levels. And so here, of course, it's n minus 1. So an s orbital is 0, a 1 is a p, a 2 is a d. so on and so forth. And then your magnetic is just, remember when we would draw an S as one line and a P as 3. So for P, L equals 1. And so then your M sub L, this is your -1, 0, and +1. Right? That's why when we got to D, we did 5, because that was from -2 to +2, because for D, orbitals L equals 2. Okay. We're comfortable? You guys know this forward and backwards? Okay. Just forwards. So the one thing we're not thinking about, that we're really not considering here, is spin. And spin doesn't really dictate any of the the wave function, because it really is, I mean, all of it's arbitrary. But spin was our spin up and spin down. So here's where we would do the M sub S quantum number, is when we were writing it like this. So ms, it's generally written as +1/2 or -1/2. Yeah?
When we're doing orbital filling diagrams, things like this, it seems to always be convention to put everything as upspin first. Does that reflect reality, or is it just...
Yeah, it does. Yeah, you're unlikely you only pair them, or you're saying like really spin up. It just could easily be spin down. Yeah, I mean, it's kind of like we could call positive and negative charge red and blue, right? Yeah. Okay. So this was just a refresher on this. And so if I gave you something like ruthenium and said, rattle off the 4 quantum numbers that are unique to ruthenium, could you do that? N equals 4. So we've got to come up with L, M sub L, and M sub S. So L equals then...
Wait, I think it's 105.
Element 104.
Right?
Should be 5, right?
Yeah. L equals 2.
So this is in a d orbital. So yes, so L is 2. Now we kind of have to sketch this out, or at least I do. So we've got how many? 1, 2, 3, 4, 5, 6. So the people would be inclined to write this as, I mean, really you have all of these options, right? But by convention you would write that as -2. And then this would be -1/2, because that electron falls as spin down. Again, arbitrary, but that's the convention. Yeah.
How did you get L equals 2?
L equals 2 is by definition the n-1. You're right. L is 4, right? But this,
Because it says here that d orbital is 2.
yeah, the d orbital is 2.
It's just that you can go up.
Because the overall, well, because the ruthenium could have, like if you were looking at the s orbital of ruthenium, then it would be different, right? So if you were talking about what is that, the electron in the 5s orbital for ruthenium, it would be that, yeah. But since we're looking at the very last electron in ruthenium, that's why it's this.
Wouldn't we say n equals 4 then? Because we're in the 4d orbital?
D is 2.
No, because you have n. Doesn't D, you have the 3d orbital and the 4d orbital?
What is the convention on that? Yeah, maybe you're right. Because the d orbitals, this is the 4d orbital, definitely. You're right. Yeah, because this is 4d6. Yeah. Okay. Yeah. Okay, so be aware that the wave function is a component then of a radial and an angular function. Okay? So because, so again, we're looking out over so think about these in terms of when we think about these in polar coordinates. The wave function can be expressed either in a Cartesian system or in a polar system, right? So when we have a polar system, instead of x, y, and z, it's r theta phi, right? So what do these two different components tell us?
What is the big letter, the Y?
A y, yeah. So the radial, this component describes the probability of finding an electron at a given distance, right? It's r. That makes sense. It is a function of the n and l quantum numbers.
Is that L and ML for angular?
L and m sub l, yes. Okay, and it's written down here. The radial functions are determined by the n and l quantum numbers. Yeah.
Oh, wait, sorry, I'm confused about this example. So is it saying that if you have a full D shell, that there's a probability that you find electrons in the f orbital, so that's how you get the L+3 component?
Say that again?
So I'm, like, usually L is n-1.
Yeah.
So I'm confused why it's 2 instead of 3.
Let me come back to that. Okay. We'll do that first thing next week. Yeah.
Because like the L, like the d orbital shell is defined to be 2. So like the s orbital is 0, d orbital is 1, and is defined to be 2. So if you have an electron in a shell that's occupying an L, so occupying a d shell, that means L is equal to 2 because your electron is occupying the shell.
Yeah, where I'm confused, where I got myself confused is that definition of that L is no, okay, so wait. L is not n equals 1. L goes up to n equals 1. Yeah, that's right, right. So L is what your orbital you are. So if you just remember SPDF is 1, 2, 3, 4, or excuse me, 0, 1, 2, 3, you're always golden.
So then I guess my question is when would you have n equals 4 or L equals 3?
When would you have L equals 4?
N equals 4 and then L equals 3.
Those F orbitals.
So that'll be like,
Right? So you would have 4 equals F, and you don't hit an F. This is the 4F, right? Yeah. So is this still right for ruthenium that 4D, yeah, 4DF. Yeah. Yeah.
I wanted to clarify on our ML number, magnetic orbital subtype. We say here that it's -2, but I've heard that you properly express that by -2 all the way up onto the same.
Yes, so what's the word for that? Degeneracy, right? That's the degeneracy of the orbital.
So why are we just saying -2 here?
I wrote it like, I've seen it done because this one falls back here. Because when you do this, when you do 6, right? So we're 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. Yeah.
So we're basically just, you have the address of the last electron.
Yeah, the address of the last electron. Yeah. Okay. Okay, so the angular function, no, we were doing radial. The distance, that was left. So that's the radial. The angular, so radial determines the distance, and then angular is what determines the shape, right? Here the function of the shape is determined by the quantum numbers L and M sub L, right? And that makes sense because we said L is spherical versus dumbbell versus donut, if you want to call it that. And then M sub L is going to be what? For a p orbital, can be -1, 0, or 1, but what does that really mean? Like, think in a Cartesian system, -1, 0, and 1 is your x, y, and z, right? That's why you have these orientations in 3 different. So people who are a lot smarter than me and have a lot more time than me have taken the time to come up with the angular functions as a function of different L and M sub L values. Okay? You would you would always have this, yeah, and it's in your text. And so here you can start to see what that means if you plotted that. So for 0, for an s orbital, it has to be 0 here. This is what the angular and, or I'm sorry, the phi and the theta equal. And as you multiply those together, you start to get this, the shape, literally the shape of that orbital. Okay? Similarly, for radial functions, here it's not a function of, it's only a function of the n and the L, right? It's not a function of m sub L, right? So that's why for a 2p orbital, it's exactly the same, right? So you have these 2 functions that are describing the location, right? One is the distance and one is the shape, okay? And then you can start to plot these. So we'll probably have a homework where so this was me convincing myself that I could actually do this and punch the math through and like make this in Excel and plot on this axis the wave function and the radial probability, right? So this squared, where a sub naught, what is a sub naught? The Bohr radius that we derived at the beginning of the class, so then you look at it as r, okay? What do you think? So then you can have these for all of these different 3s, 3p, 3d, your radial functions, and the radial probability distribution functions. What do you think's happening here? What value is that? It's going to be...
Is that like the location of the nucleus?
No, it's not the nucleus. The nucleus is going closer and closer to 0. It's where this term becomes 0. So it's where this is 2, r at any given point over the Bohr radius. It's, yeah. So when, exactly, right? So this value at 2r over the Bohr radius, that drops when, if you have 2, right? 2 minus 2 becomes 0 and the whole thing cancels out. So that's why you get nodes like this, right? That's what's happening. And it's drawn like this, but of course it's much more of a cloud. And you start to get these the nodes where there is 0 electron chance of it being there, okay? So that's a good kind of homework question too, or like thought question is, here's your equation, tell me where the nodes would be, right? Okay, we'll see you next week.